Okay, so the last two topics of the course that I need to do, and then anything else I can do on top of that will be sort of gravy, are two methods for understanding how relaxation works. Well, one is how relaxation works, and the other is how we can model, come up with a basically simple model to predict or to come up with spectral line shapes. All right, so the first one is about relaxation. And the key point here is that when you use a Schrodinger equation, it's conservative, so you don't have any way to relax. You could have energy transfer from state to state, but it would never go away. There's no dissipation. All right, so the one way to deal with this is to imagine that you have a system and that it's coupled to a bath, just like you would do in thermodynamics. And then what we do is we use a perturbation theory treatment of the interaction between the system and the bath. Okay, and then that, of course, has the usual sort of a caveats or the realms of validity. If we're using time-dependent perturbation theory, then that usually means that it won't be valid for all time, and also it needs to be weak. All right, and so you might say, well, what if it's not? Good question. Then there's ways around that, or ways to make progress. It's not easy, but there are ways to make progress. So what we're going to do is we're going to derive this theory, which is called Redfield theory. It was originally developed by Redfield to describe basically NMR spectroscopy. Of course, now we can use it for anything. And if you'll see when we're done with it, we're going to get things like population relaxation, energy transfer, dephasing, and those are the ingredients of other phenomenological models, things like the block model for two-level systems. So sometimes people will call this Bloch-Redfield theory. I don't see the need to have so many names. Basically, it's time-dependent perturbation theory for the system-bath interaction. That's as simple as that. All right, so the way we're going to do this is we're going to start with a Hamiltonian, okay? And the Hamiltonian is going to be time-dependent, of course. Right? And the usual way that we will treat this is that we're going to, so we're going to break it up into a system and a random fluctuating environment. And then we're going to describe how the system is coupled to that random fluctuating environment. Let's get started. So we start with the Liouville equation, of course. You know that we're not going to start with the Schrodinger equation because we automatically know we're going to have to lose information. So that means we're going to need a density operator. So we have the Liouville equation minus I over h bar, the commutator, right? So that's always true. For the derivation that I've been following, which I put the notes up on our Canvas site. It's due to a nice derivation by someone named van der Zwaan, who was in the old days anyway, worked with Casey Hines, was one of my all-time physical chemistry heroes. And he wrote a nice set of notes, van der Zwaan wrote a nice set of notes that helps you see how to derive the Redfield equation pretty easily. It'll probably take 2 lecture segments to do it. In those notes, they use like atomic units for the Planck's constant. Just set Planck's constant equal to 1, which means that h bar is equal to 2 pi. One over h bar is equal to 2 pi. So you end up with this. All right, so it looks basically the same. And I can put a link to the notes. They're on the internet. It's not like a secret society of people with the Redfield theory notes. All right, so we have, that means we have h equals 1, speed of light is equal to 1. We're not using speed of light, but you would. All right, so what we're going to do is partition the Hamiltonian as we've done numerous times. So you have h of t is going to be equal to h naught plus hr. Now what's the r mean? The r means the random fluctuating force. Or I should say, I can't call a Hamiltonian a force. A random fluctuating Hamiltonian. This will remind people of things like the Langevin equation, where you have a truly conservative equation of motion, like Newton's law, but then you add in a random fluctuating force that sort of plays the role of thermal excitation. All right. We're going to assume that the Hamiltonian H naught is the one that we know, the system Hamiltonian. So we have H naught has its eigenvectors n with energy levels epsilon and n. Just a warning, later on we'll drop the epsilon and just use n as the energy and the index, which is more convenient. All right. And the idea is that this is going to couple to the Hamiltonian H naught. There'll be an additional Hamiltonian term. All right, so let's write down a generic form for H naught, HR. Right. So it's going to look a little esoteric to start, but I'll try to explain what's going on there. All right, so the idea is that we have an operator here, right? Basically in the system, it operates on the system, and this is the field. All right, the field that is causing the fluctuation. When we derived the equation of motion for the density operator and then did the Dyson series and all that stuff, we introduced the interaction picture, right? We interaction picture. And so we can go back to the interaction picture for the density operator, and you end up with this kind of Liouville equation in the interaction picture. Remember that HR is like H primed in our previous notation. Now this notation's a little clunky, but bear with me. So the idea is we have the interaction picture representation of HR. So just remember that means like HR with the U naughts on the sides. U naught dagger and U naught. And then this is the interaction picture density, right? And so let's write down what that is. Interaction picture density is U naught dagger T0. So in this derivation, we're just setting T naught equal to 0. Regular density, right? If you want the Schrodinger picture density. Okay. And we remember what these are because of our units of h bar. This is going to be e to the 2 pi I h naught t rho of t e to the minus 2 pi I h naught t. Right, so just putting that in explicitly there. All right, and let's write down what the interaction picture fluctuating Hamiltonian is. All right, and that's going to be U naught HR. All right, notice we dropped the second 0. We're just sort of using just one time point for the U. If you see that, just mean it's U naught T and 0 also. All right, so this is going to be the fluctuating part. And this is just transforming it to the interaction picture. So now what we're going to do is we're going to solve the differential equation the same way we would have done if we were doing it with the Dyson series, like or with to generate the Dyson series. So you could, of course, just write that down if you want, and then just plug in the terms. That's another option. So maybe you can think of this as a review. Do you remember how to do that iterative substitutions? So if we do that, we're going to plug in, right, to our solution. We're going to have, of course, we're going to have the rho at initial time, would be one of them, minus 2 pi I, and that's the integral from 0 to t d tau HR I tau rho I tau. Okay, so that's like one iteration. And then we're going to plug in a second iteration. We're plugging back in the solution into here again. Right? That's going to cause us to have the nested commutators. So in some sense, we could have derived the response function this way. It probably would have saved a little bit of time. But I think it's more elegant to see it going to the Liouville space and then coming back and getting the commutators than just doing the Liouville equation like this. All right, so when we plug this in, and it's the same process, you just take this, plug it in, make sure that you don't lose track of the t's and the tau's. So this is the first iteration. And the second iteration might need more space, so I'll write it over here. It's going to be 2 lines because there's a lot of stuff in there. All right, so we have rho I. We still have our initial time. We have our first term, which looks the same. All right, that's our first iteration term. Then our second iteration term, we're going to plug all this in. So we'll have minus 4 pi squared, because we have the i's squared, that gives a minus 1. Then we have that. There'll be 2 integrals now. So the integral, the outer integral is 0 to t d tau, and the second one is 0 to tau. Remember how this goes? D tau prime, we need another tau. Then we have our commutator, which is HR at time t, commuting, or the commutator with HRI tau primed. Did I say t? I meant tau. Tau primed, and then rho I of 0. I'm running out of space. But at least I say it, so then hopefully it's clear what's going on. And then, of course, you could keep going and you'd have more terms, and you'd make the Dyson series, basically, for the interaction picture version. All right. Now, what have we done that's approximate up to now? Just think real quick. We have a Hamiltonian. We can break it into 2 parts. That's general. We assume the system states are stationary states. Okay, that's not a huge stretch. We have a random force. We haven't really said anything about this. You can almost imagine writing any operator like this. That doesn't seem to be too constraining. We wrote the Liouville equation. We reminded ourselves of the definitions. We plugged things in. And then if we follow the dot, dot, dot forever, then this would be exact. All right, that's absolutely true. If we stop here, we're making an approximation, right? So we stop at this point, so we stop now. So by stopping at second order, obviously we're assuming that the interaction is only good to second order. Okay, that's number 1. Now what we're going to do is we're going to say this is the state, the interaction picture version of the state, the density. We're going to now do the time derivative of this. Right, we're going to make a time equation of motion by taking the time derivative of this. It seems like we already did that. We started with that. All right, so this is the process. Make the time derivative of this approximated form of rho I. All right, so what happens when we do that? Obviously, this first term goes away. There's nothing there. And we're left with basically doing kind of the anti-integral. Sometimes they call the integral like an antiderivative. We have an anti-integral now. So by taking the time derivative, we kind of undo our integration. So we'll have minus 2 pi I times HRI of t, this must be t. Right, that's 0. That's what's in there. I made a mistake. This should be 0. Maybe someone caught that? Maybe not. I didn't. All right, minus 4 pi squared, same thing. We undo like the outer integral. So we have 0 to t. We only need 1 tau. Remember, these are just names anyway. HRI T HRI tau rho I 0. Okay, so that's an approximation, right? We made an approximation that we can stop at second order, and then we're taking the time derivative of this to give us kind of like the rate, right? This is an equation of motion, but this is an approximate equation of motion. Okay, so what's going to be the next steps? The next step that we're going to do, I have to erase, but the next step that we're going to do, I want to say it so that you'll be ready for it, is we're going to ensemble average. Right, that's an important thing because so far in everything that we've done in the class so far, we haven't done that. Sometimes there's a tendency to think of taking an expectation value that's something like an ensemble average, but that's not really the correct way to think about what an expectation value is. But here it is. Really, we're going to think about imagining that we have replicated systems that are potentially all slightly different. And what we're going to do is we're going to take advantage of the fact that we're going to impose some constraints on the fields and how they fluctuate, because that's where their time dependence, that's where the time dependence of the interaction with the environment comes. By doing an ensemble average and putting some constraints on the nature of the fluctuation, we'll be able to greatly simplify this, and we'll be able to get some quantities that tell us about the relaxation that are, I would say, rather, they become somewhat intuitive. They don't start out intuitive, but they become intuitive. So, okay, so we're going to do the ensemble averaging over the fields. So what that means is we're going to look at each of the terms. So remember, there was two basic terms, right? There was that first commutator, then there's the integral. So let's look at the first commutator. Okay, so when you have a commutator, just do it. Do what it says to do. So this will be HRI rho I minus rho I 0 HR. Okay, just to remember, this is just H rho minus rho H, and the ensemble average is a linear operator, basically, and so that means you can break it up into two ensemble averages like this. Now what we're going to do is remind ourselves, what is HRI? So HR was this sum on all these different potential interactions, like that. And although this is the interaction picture version of it, what we're looking at is essentially, so we can put that in, and then what we can remember is that there's a single time here that will be brought by putting in the U0 dagger and the U0. And then to remember that what these things really are, okay, is like a correlation function. So if I have, even in classical physics, so if I have A of t, B of 0, then what this is asking is what's the correlation, but time correlation between B0 or B of 0 and A of t. And this reflects, ensemble averaging over the whole thing. Okay, so what this is saying, if I convert this back into English, is what is the correlation in time between the initial density operator? Remember, the initial operator doesn't depend on whether it's not different if it's the interaction picture, Heisenberg picture, Schrödinger, they're all the same at 0 time. So what's the correlation between the initial density operator and the field fluctuating, the fluctuating field? Now, unless you had some totally crazy scenario where the initial value of your density operator, like how the states were distributed, affected the field fluctuations, then of course the thing I'm about to say wouldn't work. But that's not how we would want to think about this. When we think about the molecule in solution, the way the fields fluctuate does not depend on the state distribution of the molecules. Now you could think of some examples where that's not true. All right. Now that we're here, maybe I should mention this. All right. So one way it might not be true is we've talked about time-resolved fluorescence experiments in the class, right? You have a ground state, you have an excited state, you excite to the excited state. The probability of which vibrational state you end up in is dictated by the Frank-Condon factor, right? You worked out those for a model of carbon monoxide on your problem set. There'll be some relaxation in the excited state. That's a picosecond process usually. There's also going to be an environmental reorganization because you change the charge distribution in the excited state. So if you're in a solution, the solvent will move around a little bit. That would kind of shift the whole energy level away from this. Might shift the whole potential surface, right? And then eventually the system will emit light back to the ground state, and again you'll use a Frank-Condon factor to figure out the magnitude of each of the possible outcomes. All right, so this shift in the emission is called the Stokes shift, which we've discussed. And so you could imagine that if I have a ground state molecule, right, I would of course represent the density operator as like a 1 on the first element of a diagonal, on the first upper left element. But if I had an excited state molecule and I wanted to imagine what happened after I did something here, well then I have an excited state molecule. It might not be exactly the same as the fluctuation in the ground state. So you could imagine a scenario where the different populations of the states, because of their different interaction with the environment, could potentially change the nature of the interactions. But here we're mostly interested in how this will be ensemble average. In other words, if we did a very long trajectory and then we did an average over that, that's another way. If you believe the ergodic hypothesis, then an extremely long trajectory is the same thing as doing it on a bunch of molecules. Okay, so what I'm getting at, of course, is that these are uncorrelated with each other, right? You don't expect the field fluctuations to be correlated with the density operator. And this is just the same thing, but in reverse, right? So because of the lack of correlation between the initial density and the fluctuating force, or the fluctuating field, these terms are all equal to 0. All right, so the first term goes away. All right, and what we can do also is think a little bit about the how to write this down. So let's just imagine for a fluctuating variable or operator, I'll call it A here. Now, unfortunately, we don't have a lot of time to completely explore all of the amazing things you can do with time correlation functions. Sometimes you cover this in statistical mechanics, but not always, which is a little bit unfortunate. But if you have a system at equilibrium, then there will be a single value of the average of whatever quantity it is that you're considering. So this would be like an expectation value if this is a quantum mechanical operator. And then the idea is that we imagine there's a fluctuation of the value instantaneously as a function of time from this average, right? So this would look something like this. Some random fluctuation, right? And so now if I do the time correlation, or if I look at the ensemble average of A of t, this is this ensemble average of the sum of these two things. Which is the same thing as the ensemble average of the average, which of course is just the same thing as the average. And if you have a whole bunch of numbers, you take the average, fine. But then once you calculate the average, that's it. So that's the number. It's no matter what you do. And then you have the average over the fluctuating force, or the fluctuation, I should say. And of course, we're imposing that the fluctuation has an average of 0. So we insist that this is equal to 0, and this is just equal to A. All right, so this is a proof that the ensemble average of our random thing is going to be equal to the same average you would get if you could just like take a single snapshot and just look at what all the different ones were. Take the average of that. All right. So, right. Here we go. All right, so the first term goes away. So now we only have to really consider the second term. Of course, the second term is more complicated, so that means we have more work to do. So let's do the same thing for the second term. That's going to look like this. All right, so we do need to plug in the explicit form of the HR operator. That has to come, and it's coming now. All right, so when we do that, just remember we have the formula over here for what this interaction is. So let's write that now. And we know the way we're going to write this, of course, is when we see an operator, we're going to have to write that in the, remember that it's in the interaction picture for this way we're doing it, right? So we'll have, first of all, we need a sum, right? Because there's a sum of terms here. So let me put that sum out in front. And there's going to be one chunk of terms times another chunk of terms, so we're going to need 2 of these. So let's put that in right from the get-go, sum over n and m, where n and m are going to be all of the different ways that the system can interact with the environment. Most likely you can just convert this back to 1, or you could keep it more complicated later on. All right, so then we put this in, and we're going to have an, and I'm going to put the I here, an of t, because it has time dependence from doing the interaction picture, which it didn't necessarily have at the beginning, or we're assuming that it doesn't. That would be more sensible, I think. And then we have en of t. Now this is like a scalar field, right? This is not really a quantum mechanical thing. This is the quantum mechanical part here. So this is still a kind of a semi-classical, if you will, picture. All right, then we have the am for the other one, also in the interaction picture, so it has its time dependence because of that. Then it has the field part, that's the scalar, and then we have rho I of 0. Okay. All right, so far we're just plugging in. Okay, so now we're making another approximation, but this is not a bad approximation, right? What we do is we assume, okay, now that we have 2 time-dependent things in here, we need to figure out how do we deal with that, right? You don't really want to have so much correlation in here, because when you think about it, you're going to write all these terms out. There'll be 8 terms, right? And then you're going to have, we're going to have 2 terms, this times this minus this times that, right? And then we're going to have the commutator in here. And then we're going to do this ensemble average. So if we make the assumption that the field interaction picture operators, not the field, but interaction picture operators, this is, the way that we're proposing that the interaction with the environment, or that when the system fluctuates, when the environment fluctuates, what does it do to our molecules? Or what does it do to our system? We're going to assume that this which gets its time dependence from the H0 Hamiltonian, is uncorrelated to the field fluctuations or to the field itself. Okay, what that does, it allows us to factorize these ensemble averages. So instead of having to keep everything in there, we can factorize this whole thing into a part that's a correlation function of the system operators, and of course the density operator at time 0, with a product of that times the correlation function of the field itself. All right, so that means that we can go to this bit here, goes there, the minus sign, and we end up with 4 pi squared I made one mistake in here, right? Remember, this is HRI of tau. So these two need to be tau. Otherwise, we'd have the field at at the same time. That would be kind of weird. We don't want that. Okay. This is the piece that's the correlation function of the field. Then it's going to be multiplied by the correlation function of the commutator. Oh, right. We're ensemble averaging over the field, right? So we're not ensemble averaging over the operators. This stays in the form of this. Like that. Okay. So what we have now is this piece here, which is just the field. And we have this piece here, which is just the operator interacting with our initial density operator. Okay. So what we can do is we can recognize that what we really have here is a stationary ensemble average, meaning it's of an equilibrium. We've assumed that it has an equilibrium distribution. And so what you can do is you can usually show that you can make a variable shift, right? We don't need to know t and tau. We just need to know the difference between t and tau, which is to say that we can write down en t em tau, the correlation function, which is to say when we do the averaging over and over again, it doesn't matter when we start, right? That's the idea. If it did matter where we started, then it wouldn't be an ensemble or equilibrium process. Right? If you imagine that it matters when you do an experiment on Tuesday or Wednesday, then if you get different results, then of course that means the system is not at equilibrium. Maybe your laser wasn't working very well on Wednesday, but it was great on Tuesday. Well, then you might get a different spectrum on those two different days. All right, so if we assume that the system's that the bath or the fluctuating environment is at equilibrium, then that means we can replace this 2-time thing by the interval. So we'll have the value of this at 0, and this where it's t minus tau. In other words, what we're doing is we're just shifting t by subtracting, we're shifting from t to minus tau. Right, so we end up with either e of m or en, depending how you want to do it. Let me make sure I didn't get the n's and m's backwards. I don't think I did. All right, so we have this as our new correlation function. So because we only care about the interval, we could put the shift on either one of these two things, and it doesn't change the measurement of the ensemble average. So this is the same thing as writing En t minus tau Em of 0. And you pick whichever one you like better. Also, these are scalars, they're not operators, so you can write them in whatever order you want, which looks like that. All right, obviously one of these is going to be best for our derivation, one of them is not, so we'll use the one that's best. So we're going to plug this substitution into here, and that's going to give us, so equals means this thing is minus the sum on n and m 4 pi squared 0 to t d tau. And we're going to use the substitution em0 En t minus tau. That's the field part. The commutator part stays the same. All right, so the reason for this repacking is because now what we're going to do is we're going to make a variable change, okay? And the variable change that we're going to do is we're going to change the variable tau to the interval t minus tau. Okay, so when we switch it to t minus tau, what we're going to do is we're going to replace t with t minus tau. So wherever you see tau, you'll put a t minus tau. Okay, which will give us the next thing that we're going to do. This is just a time shift that we can do because of the system being at equilibrium. The next thing, and then the rest, and then math. And now the thing that we're going to do is an assumption. You want to kind of check when you do assumptions. Here what we're going to do is we're going to assume that the time correlation function of the field fluctuations, or the field itself, but that can be rewritten in terms of the fluctuations of the field, the correlation function of those fluctuations. We're going to assume that the correlation function of the field, so I'll write that as like E0 ET, is very fast. All right. In other words, we're going to assume that the correlation functions decay very rapidly. Okay, and if they decay very rapidly, what that means is if we integrate this from 0 to t, we're going to be integrating out to whatever t is. It won't make any difference if we integrate out to t or if we integrate out to infinity, because we're just adding 0 and 0 and 0 to our integral. Well, that allows us to switch this limit to infinity. That'll be important because it's going to show us, it's going to allow us to replace our integral, or realize that our integral is essentially a Fourier transform. That's not obvious yet, but it will be when we recognize that this has all these exponential terms here that come from the interaction picture. Remember, you always want to get rid at the end of the interaction picture. And what the interaction picture is going to insert for us is a whole bunch of exponentials. They're going to have different frequencies associated with them, and then that is going to let us have what would look like a Fourier transform. All right, so that's what we'll do after we erase the board.